This lesson is over rates of change. Our objective today is I can find and compare rates of change in tables, graphs, and scenarios, and we're going to look at this in linear, quadratic, and exponential situations. Now, I always like to review this characteristic because it is a basic one. You've been learning it since 8th grade, but I find that most students make mistakes on rate of change. Even when we get into more difficult characteristics like domain and range and end behavior, we still are seeing some breakdown in the rate of change aspect. So we're going to work on defining that and then try a couple examples. Remember, you're welcome to use the note-taking guide that's linked, or you can take notes on your own, but I'd recommend the note-taking guide if it's possible for you to print it out. Let's go ahead and get started. In 8th grade, a question you may have been asked, and even in 9th grade a little bit, is find the slope of between the two given points, 2, 3, and negative 5, 9. And oftentimes you would put those 2 points into a table and find the change in y divided by the change in x. Sometimes you would put them in a formula that would look like this. But still, regardless of if you have these strategies, a lot of the time students have a hard time defining what slope is actually talking about. Or they forget if they're supposed to do change in x or change in y, or does it matter which point we assign as y2 or x1. So to kind of avoid these mistakes, let's just define slope a little bit further. What does the sign of the slope tell you about the lines connecting them? Well, whenever we see a positive or a negative slope, that tells us if the line is increasing or decreasing. What does the slope of the line measure? The slope of the line measures the steepness of the line. Oftentimes I get the response that slope measures the length of the line, but it doesn't. It measures the steepness or the slope of that line. Rate of change, which again is just a synonym for slope, a rate of change compares a change in one quantity to the change in another quantity. So essentially, slope is just a ratio between two values. So let's look at slope in a bunch of different contexts: linear, quadratic, and exponential. So our first example, find the rate of change in calories burned with respect to time, calories burned per minute, if the number of calories burned follows the rule of y equals 12x plus 40, where x is the time in minutes and y is the total number of calories burned. So we're given a set of times, 20, 40, and 60, and 80 minutes, and we're going to substitute that 20, 40, and 60, and 80 into our formula to figure out how many calories would have been burned at that time. 20, and we add 40 to that, we get 280. So in 20 minutes, 280 calories are burned. When we do 12 times 40 and we add 40 to that, we get 520. When we do 12 times 60 and we add 40 more, we get 760. And then when we do 12 times 80 and we add 40, we get 1,000. So we just found our calories burned for different sections or different chunks of time. Now let's go ahead and find the slope between the intervals that are listed. So what we're doing here is called finding the average rate of change over a given interval. In this case, our first interval is from 20 to 40. So from 20 to 40, we have to find our change from 280 to 520, and our change from 20 to 40. Now finding our change in x is simple. All you have to do there is 20 to 40, and that would be an addition of 20. So our change in x is 20, and our change in y from 280 to 520 is 240. When you divide 240 by 20, you end up with 12, which is what you should have ended up with because we've got 12x as our slope. Let's look at our rate of change from 40 to 60. So our change in x from 40 to 60 is going to be 20. And then our change in y is going to be, again, 240. 240 divided by 20 gives us 12. Again, what it should have been, since our slope is a 12 and we know linear functions have a constant slope. From 60 to 80 minutes, our change is, for x's, 60 to 80 is a change of 20. And for our y's, it's a change of 240. 240 divided by 20 is 12. And then our last rate of change we're going to be looking at is from 20 to 80. So this time we're making a larger jump, 20 to 80. So our change in x from 20 to 80 is 60. And our change in y from 280 to 1,000 is 720. If you divide 720 by 60, you again get 12. So finding slope over an interval or an average rate of change is just looking at different parts of our table to determine what the slope is. We knew since our equation was linear that we should have gotten the same slope the whole time, and we did. Let's go ahead and look at quadratic now. So slope from a quadratic function. A ball is dropped from a building 180 meters high and falls at a rate of d of x equals negative 16x squared plus 180, where d of x is the distance in meters. The ball has fallen in x seconds. So know that our y value is our distance in meters, and our x value is the time in seconds. Notice how we have a function that's going to be opening down because of that negative sign, and that makes sense because we're dropping a ball off of a building. And we can already tell that the building is going to be 180 meters high. One, because it tells us in the equation, and two is because we see it as our y value, or as our y-intercept value. So what we're going to do now is we are going to substitute in the numbers 1, 2, 3, and 4 into our function, and then we're going to add 180 to it after we multiply by negative 16, that quantity squared. So you can use a calculator for this if you want. You're going to do negative 16 times 1 squared. Remember, you have to do the 1 squared first, and then we'll add 180. So 1 squared is 1 times negative 16 gives us negative 16. And 180 plus negative 16 gives us 164. So after 1 second, our ball is 164 feet in the air, meters in the air. We could fill that in here. After 2 seconds, we know we're going to have to do 2 squared, which is 4, times our negative 16. And then when we add 180 to that, we get 116. So at 2 seconds, the ball is 116 meters in the air. After 3 seconds, 3 squared is 9, times negative 16 gives us negative 144, plus the 180 we started with gives us 36. So at 3 seconds, the ball is 36 meters in the air. If we substitute a 4 in, we would do 4 squared, which is 16. So 16 times negative 16 gives us negative 256. And we add 180 to that, we get negative 76, which doesn't really help us in this table, mostly because you can't have negative 76 meters. That would imply our function is, the ball that we dropped from the building is underground. So we can kind of cross that value out of the table. You can go ahead and graph these values, and you're going to see a nice quadratic curve. You're only going to see half of it, though, because we have the other half of the parabola in the real-world context doesn't really make sense to us since our x value is time, and we can't have negative time. So we know that our curve will look something like this. It would land probably just after 3 seconds. So when we look at the slope for this one, we're finding the average rate of change from 1 to 2 seconds. So from 1 to 2 seconds, our change in x is just 1 from 1 to 2 seconds. And our change in y would be 164 down to 116, which is a decrease of 48. So our slope, or average rate of change from 1 to 2, is negative 48. Let's look at our average rate of change from 2 to 3 seconds. We know our change in x is a positive 1, and then our change in y is the 116 down to 36, which is a decrease of 80. So our average rate of change here is negative 80. Our average rate of change from 1 to 3 seconds, that's where we're making just a larger jump from 1 to 3. Our change in x is 2, from 1 to 3 is 2. And our change in y would be our 164 down to 36, which is a subtraction of 128. 128 divided by 2 gives us negative 64. So as you can see, our rate of change, our average rate of change for our quadratic functions is all different. And we knew that was going to be true because quadratic functions do not have a constant rate of change. Let's look at our last example. This is going to be an example that we're going to kind of look at the average speed of a trip home, and we'll kind of talk about some questions to kind of follow up and relate it to the real world. So our x value is time in hours, and our distance is in miles. So we're going to find our average speed from different intervals. So from 0 to 1, when x is 0 to x is 1, our change in y is going to be plus 40. Our change in x is going to be 1. So our average speed from 1 hour or from 0 hours to 1 hour was 40 miles per hour. Let's look at our average rate of change from 1 to 2. From here, our change in x would be a 1, and our change in y would be a plus 60. So our average speed from hours 1 to 2 was 60 miles per hour. Let's look at our average rate of change from 4 to 5. Our change from 4 to 5 is 1, our change in x, and our change from 230 to 300 is 70. So our average rate of change from hour 4 to hour 5 was 70 miles per hour. And then we're going to look at our average rate of change from 6 to 8. So our change from 6 to 8 is a plus 2, and our change from 330 to 400 is 70. 70 divided by 2 gives us 35. So our average rate of change from x equals 6 to x equals 8 is 35 miles per hour. Our last one is we're going to find our average speed of our trip from x is 0 to x is 8. So we're jumping our whole table right here from 0 to 8. So from there, we would say that our average, or our change in x is 8 from 0 to 8, and our change in y is 400. And if you do 400 divided by 8, similar to if you did 40 by 8, you're going to get 50, except you drop the 0 if you're doing 40 by 8. So the average speed from 0 to 8 hours would be 50 miles per hour. But the question is, did I drive that speed the whole way home? Did I drive 50 miles per hour the whole way home? My answer is no. I just showed that I drove 40 miles per hour at some point. I averaged 60 miles per hour, 70 miles per hour, 35 miles per hour. It really just depends on which which x values you're looking at. So no, we didn't drive 50 miles an hour the whole way home. That was just an average of the entire trip. So knowing that, which sentence makes a little more sense to say? Does it make more sense to say I drove home at 50 miles per hour? Or does it make sense that I averaged 50 miles per hour on my drive home? The answer is that I averaged 50 miles per hour on my drive home. This is an average because we're finding an average rate of change for the entire trip, 0 to 8 hours. We found individual averages from different sections of hours, but if we average all of those together, we would get 50 miles per hour.